Welcome. In this video, we will explore the fundamental concepts of vector algebra, which are essential for the IB Mathematics Analysis and Approaches higher-level curriculum. By the end of this session, you will be able to: first, understand and apply the key properties of vector addition and scalar multiplication. Second, solve vector equations using these properties. And third, calculate the displacement vector between 2 points and its magnitude, both in 2 and 3 dimensions. Let's begin by establishing the basic rules that govern vector operations. Our first objective is to understand the properties of vector addition and scalar multiplication. These properties are very similar to those you've used with real numbers, but it's important to see how they apply to vectors. Let's consider 3 general vectors in 3-dimensional space: A, B, and C, and a scalar k, which is a real number. The first property is the commutative property of addition. This states that the order in which you add 2 vectors does not change the result. In other words, A plus B equals B plus A. We can prove this by adding the component vectors. A plus B is the vector, A1 plus B1, A2 plus B2, A3 plus B3. And B plus A is the vector, B1 plus A1, B2 plus A2, B3 plus A3. Since addition of real numbers is commutative, A1 plus B1 is the same as B1 plus A1, and so on for all components. Therefore, the 2 vectors are equal. The order of addition does not matter. Next, we have the associative property of addition. This property tells us that when adding 3 or more vectors, the way we group them doesn't affect the final sum. So, A plus B plus C is the same as A plus B plus C. Let's prove this. First, let's calculate the left-hand side. The vector A plus B is A1 plus B1, A2 plus B2, A3 plus B3. Adding C to this gives us A1 plus B1 plus C1, A2 plus B2 plus C2, A3 plus B3 plus C3. Now for the right-hand side. The vector B plus C is B1 plus C1, B2 plus C2, B3 plus C3. Adding A to this gives us A1 plus B1 plus C1, A2 plus B2 plus C2, A3 plus B3 plus C3. As you can see, both sides are identical. This confirms that vector addition is associative. The grouping of vectors in a sum does not change the result. Next, we have the additive identity property. This property introduces the zero vector, denoted by a bold 0. It states that adding the zero vector to any vector A leaves the vector unchanged. So A plus the 0 vector equals the 0 vector plus A, which equals A. The 0 vector is simply a vector where all components are 0. In 3 dimensions, the 0 vector is 0, 0, 0. If we add this to vector A, we get a 1 plus 0, a 2 plus 0, a 3 plus 0, which simplifies to a 1, a 2, a 3, which is just vector A. This confirms the property. Closely related is the additive inverse property. For every vector A, there exists an additive inverse, negative A. When you add a vector to its inverse, the result is the 0 vector. So A plus negative A equals negative A plus A, which equals the 0 vector. The vector negative A is found by negating each component of A. So negative A is the vector, a 1, a 2, a 3. Adding A and negative A gives a 1 minus a 1, a 2 minus a 2, a 3 minus a 3, which is the 0 vector, 0, 0, 0. This property is crucial for solving vector equations. Now let's look at properties involving scalar multiplication. First, the distributive property. This property states that a scalar k can be distributed over a sum of 2 vectors. So k times the quantity A plus B is equal to k times A plus k times B. Let's prove this by working with the components. The left-hand side is k times the vector, A1 plus B1, A2 plus B2, A3 plus B3. Multiplying the scalar k into each component gives us KA1 plus B1, KA2 plus B2, KA3 plus B3. Using the distributive property for real numbers, this becomes Ka1 plus KB1, Ka2 plus KB2, Ka3 plus KB3. We can split this into two separate vectors, k1, k2, k3, plus kb1, kb2, kb3. And this is exactly k plus kb, so the distributive property holds for vectors. The final property we'll cover today relates to the magnitude of a scalar multiple of a vector. This property states that the magnitude of k times a vector a is equal to the absolute value of the scalar k, multiplied by the magnitude of the vector a. In other words, the length of the new vector is the absolute value of k times the length of the original vector. Let's prove this using the formula for the magnitude of a vector. The magnitude of vector a is the square root of the sum of the squares of its components. The vector k is k1, k2, k3. So the magnitude of k is the square root of k1 squared plus k2 squared plus k3 squared. This simplifies to the square root of k squared times a 1 squared plus a 2 squared plus a 3 squared. We can take the k squared out of the square root, which gives us the absolute value of k. What's left inside the square root is the magnitude of a. So we have proven that the magnitude of k is the absolute value of k times the magnitude of a. This property also tells us that the vector k is parallel to the vector a. If k is positive, they point in the same direction. If k is negative, they point in opposite directions. Now that we understand these properties, we can use them to solve vector equations. This is our second objective. The rules for solving vector equations are very similar to those for solving real number equations. However, there is one crucial difference. You cannot divide a vector by a scalar. The expression a divided by k has no meaning in vector algebra. Instead, we multiply by the reciprocal scalar. For example, if we have 2x equals a, we don't write x equals a over 2. Instead, we multiply both sides by the reciprocal of 2, which is 1/2. This gives us x equals 1/2 a. Let's look at two useful rules that come directly from the properties we just discussed. First, if x plus a equals b, then x equals b minus a. We can prove this by adding the additive inverse of a to both sides. We add negative a to both sides. On the left, a plus negative a becomes the 0 vector. On the right, we have b minus a. So x plus the 0 vector equals b minus a, which simplifies to x equals b minus a. Second, if x equals a, where k is not 0, then x equals 1 over k times a. We prove this by multiplying both sides by the reciprocal of k. Multiplying both sides by 1 over k, we get 1 over k times k. X equals 1 over k times a. On the left, 1 over k times k is 1, so we have 1x, which is just x. This gives us x equals 1 over k times a. These two rules are the foundation for solving most vector equations. Let's work through some examples to see these rules in action. We'll start with a simple one. Suppose we need to solve the equation 3x minus r equals s for the vector x. Our goal is to isolate x. First, we need to move the vector r to the other side. We can do this by adding r to both sides. Adding r to both sides gives us 3x equals s plus r. Now we have 3 times x equals the vector s plus r. To find x, we need to get rid of the scalar 3. We do this by multiplying by its reciprocal, 1/3. Multiplying both sides by 1/3 gives us x equals 1/3 times the quantity s plus r. This is our final answer. Let's try another one. This time, let's solve c minus 2x equals d for x. Again, we want to isolate x. Let's start by moving the vector c to the right side by subtracting it from both sides. This gives us negative 2x equals d minus c. Now we have negative 2 times x. To solve for x, we multiply by the reciprocal of negative 2, which is negative 1/2. Multiplying both sides by negative 1/2 gives us x equals negative 1/2 times the quantity d minus c. We can also distribute the negative sign to write this as x equals 1/2 times the quantity c minus d. Both forms are correct. Let's work through a more concrete example with specific vectors. Suppose we are given two vectors, a equals -1, 2, 3, and b equals 2, -2, 1. We want to find the vector x that satisfies the equation 3x minus a equals 2b. First, let's solve the equation for x algebraically. Just like we did before, we add a to both sides to get 3x equals 2b plus a. Then we multiply by 1/3 to get x equals 1/3 times the quantity 2b plus a. Now we can substitute the actual vectors and calculate the result. First, let's find 2b. That's 2 times the vector. 2 minus 2, 1, which gives us 4 minus 4, 2. Next, we add a to this result. 4 minus 4, 2, plus minus 1, 2, 3, gives us 3 minus 2, 5. Finally, we multiply this vector by 1/3. 1/3 times 3 minus 2, 5, gives us the vector 1 minus 2/3, 5/3. So the vector x is 1 minus 2/3, 5/3. Now we move to our third objective, finding the vector between 2 points. This is a fundamental concept in coordinate geometry. Let's consider 2 points, A and B, in a coordinate system. The position vector of a point is the vector from the origin to that point. So if point A has coordinates a1, a2, its position vector, which we write as OA or just A, is a1, a2. Similarly, if point B has coordinates b1, b2, its position vector OB or B is b1, b2. We want to find the displacement vector from point A to point B, which we write as A, B. This vector represents the translation needed to move from A to B. Using the triangle law of vector addition, we can see that the vector A, B is equal to the vector AO plus the vector OB. Remember that the vector AO is the negative of the position vector A. So A, B equals negative A plus B, which we can rewrite as B minus A. This is a crucial formula. The vector from A to B is the position vector of B minus the position vector of A. In terms of components, this means we subtract the coordinates of the starting point from the coordinates of the ending point. So AB is the vector, B1 minus A1, B2 minus A2. This rule extends directly to 3 dimensions. If A is A1, A2, A3, and B is B1, B2, B3, then AB is B1 minus A1, B2 minus A2, B3 minus A3. Let's apply this formula with a 2D example. Given points A, -1, 2, and B, 3, 4, let's find the displacement vector from A to B, which is AB. Using our formula, A, B equals the position vector of B minus the position vector of A. The position vector of B is 3, 4, and the position vector of A is -1, 2. Subtracting the components, we get 3 minus 1, 4 minus 2, which simplifies to 4, 2. So the vector AB is 4, 2. This means to get from A to B, you move 4 units in the x direction and 2 units in the y direction. Now for a 3D example. Let's find the vector PQ given points P minus 3, 1, 2, and Q1 minus 1, 3. Again, we use the formula PQ equals the position vector of Q minus the position vector of P. The position vector of Q is 1, minus 1, 3, and the position vector of P is minus 3, 1, 2. Subtracting the components, we get 1 minus 3, minus 1 minus 1, 3 minus 2, which simplifies to 4 minus 2, 1. So the vector PQ is 4 minus 2, 1. Once we have a vector, we can find its magnitude, or length. This is a direct application of the Pythagorean theorem. For a 2D vector, v equals v1, v2, its magnitude, written as, is the square root of v1 squared plus v2 squared. For a 3D vector, v equals v1, v2, v3, its magnitude is the square root of v1 squared plus v2 squared plus v3 squared. Let's find the magnitude of the vector PQ we just calculated. we found that PQ is the vector 4 minus 2, 1. The magnitude of PQ is the square root of 4 squared plus negative 2 squared plus 1 squared. This is the square root of 16 plus 4 plus 1, which equals the square root of 21. So the distance between points P and Q is the square root of 21 units. Let's try another example. Suppose we have points A, 2, 3, and B, 6, 2. First, we find the vector AB. It's 6 minus 2, 2 minus 3, which is 4 minus 1. Now, we find its magnitude. The magnitude of AB is the square root of 4 squared plus negative 1 squared. This is the square root of 16 plus 1, which is the square root of 17. The distance between A and B is the square root of 17 units. Let's explore how these concepts apply to geometric shapes, starting with triangles. Consider a triangle with vertices A, B, and C. We can represent its sides using vectors. For example, the vector AB goes from A to B, BC from B to C, and CA from C to A. A key property of vectors in a closed loop, like a triangle, is that their sum is the zero vector. So AB plus BC plus CA equals the zero vector. This makes sense as you end up back where you started. We can rearrange this equation to find relationships between the vectors. For instance, we can write BC equals negative AB plus AC. This means the vector from B to C is the same as going from B to A, and then from A to C. Let's use this in an example. Given a triangle with vertices A, 1, 2, B, 3, 5, and C, 4, minus 1, let's find the vector BC. We'll use the relationship BC equals AC minus AB. First, we need to find AC and AB. The vector AB is 3 minus 1, 5 minus 2, which is 2, 3. The vector AC is 4 minus 1 minus 2, which is 3 minus 3. Now we can find BC by subtracting AB from AC. BC equals 3 minus 3 minus 2, 3, which gives us 1 minus 6. We can check this by calculating BC directly from the coordinates of B and C. BC equals 4 minus 3 minus 1 minus 5, which is 1 minus 6. The answers match, confirming our method. Let's look at another common geometric problem, finding the coordinates of a point that divides a line segment in a given ratio. Suppose we have a line segment AB, and a point M lies on it, such that the ratio of the length AM to MB is M to N. This means that the vector AM is a scalar multiple of the vector AB. Specifically, AM is equal to the fraction M over M plus N times the vector AB. We can use this to find the position vector of M, which we'll call M. The position vector M is the position vector of A plus the vector AM. Substituting our expression for AM, we get M equals A plus M over M plus N times the quantity B minus A. Rearranging this gives us the section formula M equals N times A plus M times B all over M plus N. This formula is very useful for finding the coordinates of a point that divides a segment in a specific ratio. A special case is when M is the midpoint of AB. In this case, the ratio is 1 to 1, so M and N are both 1. The midpoint formula becomes M equals A plus B over 2. This means the position vector of the midpoint is the average of the position vectors of the endpoints. Let's apply the midpoint formula to an example. Suppose we have a triangle with vertices C, minus 4, 1, B, minus 1, 2, and A, 3, 6. Let M be the midpoint of the side AB. We want to find the coordinates of M. We use the midpoint formula, which states that the position vector of M is the average of the position vectors of A and B. So M equals 1/2 times the quantity A plus B. Substituting the position vectors, we get M equals 1/2 times the vector 3, 6, plus the vector minus 1, 2. Adding the vectors inside the parentheses gives us 2, 8. Multiplying by 1/2, we get the vector 1, 4. Since the position vector of M is 1, 4, the coordinates of the midpoint M are 1, 4. The problem also asks us to verify a vector identity. We need to show that the vector Cm is equal to 1/2 of the vector Ca plus 1/2 of the vector Cb. Let's calculate the left-hand side. Cm. Cm is the position vector of M minus the position vector of C. That's 1, 4, minus 4, 1, which gives us 5, 3. Now let's calculate the right-hand side. First, we need Ca and Cb. Ca is A minus C, which is 3, 6, minus 4, 1, giving 7, 5. Cb is B minus C, which is minus 1, 2, minus 4, 1, giving 3, 1. Now we can calculate the right-hand side. 1/2 Ca plus 1/2 Cb is 1/2 times 7, 5, plus 1/2 times 3, 1. This is 3.5, 2.5, plus 1.5, 0.5, which equals 5, 3. Since both sides are equal to 5, 3, the identity is verified. This identity is a vector form of the midpoint theorem. Let's now apply these ideas to parallelograms. A parallelogram is a quadrilateral with two pairs of parallel sides. This property is key. The vector representing one side is equal to the vector representing the opposite side. For a parallelogram ABCD, the vector AB is equal to the vector DC. We can use this property to find the coordinates of a missing vertex. Consider a parallelogram ABCD with vertices A, minus 1, 2, 1, B, 2, 0, minus 1, and D, 3, 1, 4. We need to find the coordinates of the fourth vertex, C. Let the coordinates of C be A, B, C. Since ABCD is a parallelogram, the vector AB must be equal to the vector DC. So we set up the equation AB equals DC. First, let's find the vector AB. AB is B minus A, which is 2 minus 1, 0 minus 2, minus 1 minus 1, giving us the vector 3 minus 2 minus 2. Next, let's find the vector DC. DC is C minus D, which is A minus 3, B minus 1, C minus 4. Now we equate the two vectors. We have A minus 3, B minus 1, C minus 4 equals 3 minus 2 minus 2. For two vectors to be equal, their corresponding components must be equal. This gives us a system of three equations. A minus 3 equals 3, so A equals 6. B minus 1 equals minus 2, so B equals minus 1. And C minus 4 equals minus 2, so C equals 2. Therefore, the coordinates of vertex C are 6, minus 1, 2. A great way to check your answer is to use the property that the diagonals of a parallelogram bisect each other. This means they share the same midpoint. Let's find the midpoint of the diagonal DB. It's 3 plus 2 over 2, 1 plus 0 over 2, 4 plus minus 1 over 2, which is 2.5, 0.5, 1.5. Now let's find the midpoint of the diagonal AC using our calculated coordinates for C. It's minus 1 plus 6 over 2, 2 plus minus 1 over 2, 1 plus 2 over 2, which is also 2.5, 0.5, 1.5. Since the midpoints are the same, our answer for C is correct. Let's conclude with a problem that combines several of these concepts. Suppose the line segment PQ is the diameter of a circle with center C, 1, 2. We are given the coordinates of one endpoint, P minus 1, 1, and we need to find the coordinates of the other endpoint, Q. Since PQ is the diameter and C is the center, C must be the midpoint of the segment PQ. This means we can use the midpoint formula. The position vector of the center, C, is the average of the position vectors of the endpoints, P and Q. We know C and P, and we want to find Q. Let's rearrange the formula to solve for Q. Multiplying both sides by 2 gives 2C equals P plus Q. Subtracting p from both sides gives q equals 2c minus p. Now we can substitute the position vectors. Q equals 2 times the vector 1, 2, minus the vector minus 1, 1. This is 2, 4, minus 1, 1, which gives us the vector 3, 3. Therefore, the coordinates of the other endpoint Q are 3, 3. Let's quickly recap what we've covered. We started by establishing the fundamental properties of vector algebra, including the commutative, associative, identity, and inverse properties for addition, and the distributive and magnitude properties for scalar multiplication. We then use these properties to solve vector equations, emphasizing that we multiply by reciprocals instead of dividing. Finally, we learned how to find the displacement vector between 2 points and its magnitude, and applied these concepts to solve problems involving triangles, parallelograms, and midpoints. You are now equipped to understand and apply the key properties of vector operations, solve vector equations, and calculate displacement vectors and their magnitudes. These skills are foundational for more advanced topics in vector geometry. To solidify your understanding, here are 5 practice questions in the style of IB assessment. Pause the video, work through them, and then resume to see the fully worked solutions. Question 1. Given vectors a and b, find the vector x that satisfies the equation 2x plus 3a equals b. Question 2. Points P and Q have position vectors P and Q. Find the vector PQ and its magnitude. Question 3. The vertices of a triangle are A, B, and C. Find the vector BC and the length of the side BC. Question 4. ABCD is a parallelogram. Given the coordinates of A, B, and C, find the coordinates of the fourth vertex, D. Question 5. The line segment AB is the diameter of a circle with center C. Given the coordinates of A and C, find the coordinates of the other endpoint, B. Welcome back. Let's go through the solutions. For question 1, we need to solve 2x plus 3a equals b. Rearranging for x, we get x equals 1/2 times the quantity b minus 3a. First, we calculate 3a, which is 3 minus 6, 9. Then, we subtract this from b. 4, 1 minus 2 minus 3 minus 6, 9 gives 1, 7 minus 11. Finally, we multiply by 1/2 to get our answer for x. 1/2, 7/2 minus 11/2. For question 2, we find the vector PQ by subtracting P from Q. This gives us minus 3, 3, 6. The magnitude of PQ is the square root of minus 3 squared plus 3 squared plus 6 squared, which is the square root of 54. This can be simplified to 3 times the square root of 6. For question 3, the vector BC is C minus B, which is 3 minus 4. The length of BC is the square root of 3 squared plus minus 4 squared, which is the square root of 25, or 5. For question 4, we use the property that AB equals DC. This gives us the equation 3 minus 1 equals 4 minus D1, 3 minus D2, minus 2 minus D3. Solving for the components of D, we find D is 1, 4, 3. For question 5, C is the midpoint of A, B. We use the formula Q equals 2C minus page. Substituting the vectors, we find that the position vector of B is 5 minus 5. So, the coordinates of B are 5 minus 5. I hope this video has helped you understand the fundamentals of vector algebra. Keep practicing these concepts, as they are essential for success in IB mathematics, DAHL,